Okay, good morning, students. Welcome to the today's class. Yesterday we have seen the counters, right? Yeah. So in the counters, counter is one of the sequential circuit. This can be implemented with the help of the state diagram, and each and every component in the state diagram has shown in this particular diagram. And we have already written the code. One important point I want to discuss here is that since we are writing the output as a assignment statement, it is simply an assignment statement, right? The key should not be written in the form of register data type. That's what yesterday I would like to discuss about it. Okay. So except this point, everything is okay. This is from 2 down to 0 of Q. Okay. Okay. So if Q is available, if it is there in this particular always blocks, anywhere in this two always block, then we should write it as a register data type. Otherwise, it's not necessary. We should not write in the form of a register data type. Simply it is a assignment statement. Okay, agreed? Okay. My voice is clear to everyone? Please let me know. Students, please respond.
Yes, sir.
Okay. It is sorry. It is the lecture number 15, right? So we would like to discuss about, for example, finite state machines. Okay. FSM. It is a finite state machines. It is also a very important concept in order to realize a complete digital system. Okay. Let us recapitulate what we have seen in the last class. Okay. So the counters that we have introduced. Okay. The counters also different ways that we can do either sequential, either a asynchronous counter or a synchronous counter. Yeah, it doesn't have any. We can identify that one by using the always statement command. If, for example, if it is a synchronous counter, okay, synchronous counter. If it is a synchronous counter, just we have to say that always statement we have to use, and at the rate of only passage of the clock only we will write passage of, or whatever may be the thing it is, it doesn't matter. So it is a clock signal only we have to consider. Okay. So this is what we have to consider for if in the case of asynchronous counter, which means that the clock is synchronization with the clock is in asynchronous to the reset signal. Okay. So there we have to use the positive edge of the reset signal or and as well as positive of RST. So this is also involved in this one. Okay. I hope the point is clear to everyone. So we have been discussing about these concepts previously. You should be in a position to understand this one. If not, please refer the classes previously discussed. Okay. Okay, this is the way that we can differentiate asynchronous counter and asynchronous counters in Verilog point of view. Okay, in digital point of view, we can represent the same clock for all the flip-flops is a synchronous counter. If the same clock is not there and output of the preceding stage clock is preceding output is connected as a clock to the succeeding stage, then it is called as synchronous counter. This differentiation is identified in the Verilog by using the always statement, something like this. Agreed? Okay. So and also we have done the synchronous counters in different way. It may be a synchronous or asynchronous, it doesn't matter. A complete sequence, for example, continuous sequence, for example, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 0. Okay, so this is called a continuous sequence. We can generate this one. It is possible to generate one way, or otherwise something like this also we can do this one. maybe whatever it may be the case. So how much, what is the size of the, oh, so what is the size of the uh, counting is not a matter for us. A required count is also possible to generate. Okay. Okay. So these are the two ways that I can do. Okay. So sometimes we can call it as this. This is more suitable to say that it is a mod 7 counter. Okay. So 7 counts it can perform. Okay. Otherwise, a mod 8 counter. Okay. Or mod 16 counter, mod 16 or mod 60. Okay. Okay, so depending upon this one, we can generate the continuous counting sequence. Okay, but it is also possible to generate the counting sequence required to us. Clear to all of you? So these are the things that we have discussed previously. Okay, and one more thing is that whenever we are designing this kind of thing, we have used the structural modeling. Okay, behavioral modeling, complete behavioral modeling that we have seen. Behavioral modeling. Okay, so in the behavioral modeling, directly I have used the count is equal count plus one. Antena, Q is equal to Q plus one is the concept logic that I have used there. But here in the behavioral modeling, behavioral, it is also possible to write the behavioral modeling in this particular cases also. But remember that we have used the two always statement, two always statements. Okay, so the always statement is possible to write the continuous sequence also. Okay, so ఇక్కడ కూడా మనం రాయొచ్చు two always statements. అంత అవసరం లేదు, డైరెక్ట్ గా ఉంది కాబట్టి intelligent way that we have to write all the time. But in the second case, there is no choice, we have to use two always statements. Okay, so it's just like a two blocks are available, each block I'm writing in the form of a always statements. Okay, it is sometimes look like a structural modeling only. Okay, but it's not the structural modeling. In fact, I'm telling you frankly, it's a behavioral modeling, but I'm using the two always statements. Okay. So with this concept, okay, we will okay, FSM, finite state machine. Okay, so these are very important. The design, the finite state machines are very important to realize the control unit of a digital system. Okay, so far we have seen any digital system. Okay, whereas write a digital system, So this digital system can be viewed depending upon the output. Okay, so it is a combinational digital circuit, maybe a combinational digital circuit. Okay, or it may be a sequential digital circuit. Okay, so this is the general view of representing the thing. Okay, another method is also there. This is called the data path unit. So the digital system can be considered as a data path unit, and it is a control unit. Okay, any digital system can be represented by using these two components. Okay, so what for this data path unit? It is for the circuit realization. Okay, hardware representation. Okay, it's not better way. Data path unit is the arithmetic operations or operations will be performed on the data path. Okay, for operations. So what for this is control the operations. Okay, so for example, we have addition, subtraction, multiplication, division, or something is there. So at what time addition has to perform, at what time the subtraction has to perform, what time the division has to perform. All this is controlled or sequenced by the control unit. Okay, so therefore, if you talk about a very large digital circuit, if it is a large digital circuit, generally it consisting of a data path unit and control unit. Usually, this control unit is nothing but a sequential circuit. It is nothing but a sequential digital system. Okay, so the control unit is most of the cases it is a digital system. So data path unit is most of the cases. It's not obvious. Most of the cases it is used in the data path unit. Because it is only the outputs depending upon the present input conditions. But control unit is not like that. The control sequence is depending upon what we have done previously. So that's what it's depends upon, right? So this is all about the digital systems concept. Okay, so therefore we would like to discuss about the finite state machines in order to realize the control unit. Agreed? So here is the concept is involved in the finite state machine. Here we talk about FSMs. So for realization of the control unit, most of the cases we use finite state machines. Okay, okay, fine. I'm not going to go for more detail about how digital system is represented by the data path unit and control unit at this moment. We will talk about later on. For the time being, let us consider a sequential circuit. Okay, a sequential circuit, sequential finite state machine. Okay. Usual example we would like to give is sequence detector. Sequence detector. Okay, so this is the one of the sequential circuit. Okay, this can be represented by the finite number of steps. Okay, why this name has come into the picture? The reason is that if you want to represent any digital system, we would like to use only finite number of state. Okay, so we use finite number of states to represent digital system, to represent the digital system. Okay, so this is what actually the meaning of finite state machine. Okay, so let us consider this is a one digital system, that too a sequential circuit, that too a sequential circuit. Okay, how this digital system is represented by finite number of states. Of course, so the counter is also a sequential circuit. As I mentioned that the counter is also a sequential circuit. How many number of states that can decide the counter? For example, the 7-bit counter I have used, sorry, 3-bit counter I have used here. So these are the finite number of states that are required to completely define the counter. Okay, so therefore it is a simply a finite state machine. Okay, we can write it like that. Okay, but let us consider the sequence detector also with the help of finite number of states. Okay, so that means first of all we would like to discuss about what is the top module or top level circuit for this sequence detector, what it will produce. Okay, a sequence detector having only single input and it will produce single output. Okay, but the inputs are coming. Okay, not only not necessary that a single input, but one case that we are considering, so multi input is also possible. Okay, I have an X input here, I have a Y output here. If I'm applying the input is equal to 0, okay, so I would like to detect for example 1 0 1 0 sequence, for example. Okay, 3 is not required, let us consider 3 bits. Okay, now I want to define, I want to discuss about, I want to detect I have a set of inputs here. Okay, 0 0 1 0 1 1 0 1 0 1 0 0 0 1 0, something like a set of inputs are coming, set of bits are coming one by one. Okay, so I want to discuss about the output only if continuous sequence of 101 is observed. Okay, so this continuous 101 is observed in this furnace. Here is observed here. Here, what is observed? Here it is observed. Okay, next here also it is observed. Here is also is observed. So observe very carefully. Here is the overlapping is observed. Overlapping. Okay, that means in order to see that particular set of bits, okay, previous bit also need to be considered sometimes. Okay, this is called overlapping. Sometimes non-overlapping is also considered. That means once the 3 bits are completed, we have to start a new sequence from the 4th bit onwards. So these are called non-overlapping sequence. Non-overlapping sequence. If it is a, for example, if I consider the non-overlapping sequence, means this is the one sequence. The 0, 1, 1 is the next sequence. Okay, 0, 1, 0 is the next sequence. 1, 0, 0 is the next sequence, something like this. And this is also another sequence. All right. But in overlapping sequence, so it's a better example I'm considering here. Okay, so we most of the cases we would like to take the overlapping sequence than that of non-overlapping sequence. So what is the output that we will get if it is a overlapping sequence? If first bit is 0, therefore 3 bits are not completed, the output is also 0. 3 bits are not completed, 3 bits completed, but it's not the actual sequence, the 0. And we would like to consider about the next one. These 3 considered, not possible. Next, these 2 are considering, yes, it is possible. So next, these 3 are considering, not possible. So like this we can generate, but it's so overlapping sequence, all are zeros only, all are zeros only, because no 3 bits has got 101 sequence if you consider the 3 bits. Okay, I think better I'll write it here so that you won't have any problem with that. So this is what I have given. So 3 bits complete avvaledu kada, 0 0 3 bits complete అయిపోయినాయి ఇక్కడికి, but still I didn't get 101 sequence, therefore the output is also 0. Now ఇక్కడ నుంచి స్టార్ట్ చేద్దాం. ఇక్కడ నుంచి స్టార్ట్ చేస్తే ఏమవుతుంది, మనకి అయినా కూడా నాకు సీక్వెన్స్ రాలేదు కాబట్టి ఇక్కడ అవుట్పుట్ ఇస్ 0. మనం ఎక్కడి నుంచి స్టార్ట్ చేద్దాం, అవుతుందా ఇప్పుడు? ఆర్ వి గెటింగ్ దీస్ 3 హియర్ నౌ? దిస్ ఇస్ వాట్ ఐఎమ్ టాకింగ్ అబౌట్. yes, the output is 1. Next one is these 3, not there. These 3, not there. Yeah, these 3, are we getting this one? Yeah, this is the sequence, we can get it there. This is the one. Okay, now next, these 3, we don't get output. These 3, yes, there is a possibility of overlapping sequence is also considered, therefore we will get the output is equal, logic 1. These 3, not possible. These 3, not possible. These 3 cannot be detected. These 3 cannot be detected. These 3 cannot be detected. So this is what we observed the output sequence. So therefore here is the only cases in a sequence. These are the positions where I got the output value is 1. So therefore this is what we would like to write output of the overlapping sequence. This is the output of the overlapping sequence for the given input. Agree? So if non-overlapping sequence, it is overlapping. What about non-overlapping sequence? We have to consider continuous 3 bits. So these 3 bits we considered, the output is 0 0 0 0. Next we have to consider these 3 bits. Okay, 0, sorry, 0 0 0. Next we have to consider these 3 bits. Again this is 0 0 0. So again what we have to do, consider 3. Therefore this is also 0 0 0. Therefore, next bit is also 0, 0. That means this particular detector, sequence detector, is not able to identify 101 sequence as 101 sequence. Why? Because it is a non-overlapping sequence. Okay. So therefore, what type of sequence detector they're asking in the examination, that we have to consider. Okay. Okay, so the way I am presenting the output is not the better way. Okay, so it is very easy to identify the output with the help of state diagrams. Okay, the state diagrams are very important now. Okay, using the state diagrams, I am able to define the output in a systematic manner by using the finite number of states or state diagram. Okay, so that means I have a 101 sequence is there in my hand. Okay, assume that I have a this particular sequence is coming first, this particular bit is coming first. Okay, okay. So for example, the state of the system is S naught. What do you mean by the state of a system? The content available in the memory. The content available in the memory. Right? So this is called the state of the system. Okay. So if any digital system, or I can say that, for example, here we considered a digital system. Okay, digital system. Initially, one is coming here. Is this one can affect the digital system so that it will produce the output? That's the question. That means whenever you are applying some input bit, that bit is able to change the state of the digital system or not, we need to check. Right? Okay. Okay. So yes, logic 1, if you apply to the digital system, is able to change the state of a digital system. Why? Because 1 is a valid bit in a given sequence. 1 is a valid bit. So the one word we am talking about, valid. Valid bit is the one word I'm writing. Okay. Okay. For example, 0 has come. For example, instead of 1, 0 has come. For example, instead of 1, it is 0 come. 0 come. Is it a valid bit in a given sequence? So this is my given sequence is this one. Okay. The starting must be 1 ఉండాలి. 1 వస్తే valid bit అని చెప్పాను. అదే 1 బదులు 0 వచ్చింది అనుకోండి, నేను అప్లై చేసిన ఇన్పుట్. ఫర్ ఎగ్జాంపుల్, దిస్ ఇస్ మై ఇన్పుట్, రైట్? This is my input X. I'm applying externally. Okay, here is the 101 is available here. So therefore, here I don't have any problem. 1 is there, therefore 1 is yes, this one is a valid bit to this digital system. But instead of this one, 0 has come first here. Is it a valid bit in this given sequence? No. Therefore, what we can say that not valid. Not valid bit. So these are the two terms that we have to remember. In this particular sequence, okay, 1 is a valid bit, 0 is a non-valid bit. For example, the sequence I am changing. For example, 100 sequences I am giving here. Okay, now I'm applying the X here. I'm sending the logic 1 first time. What we can call, is it a valid bit in this sequence or not valid bits in the sequence? Anyone from the class? Are you following the class?
Valid bit, sir.
Please remember, I'm talking that first bit is LSB bit actually. First bit is LSB. If the first bit is a logic 0, that means it's not a valid bit now here. It's not a valid bit. I'm particularly said it is a LSB bit. So according to the first is a LSB bit means I talk about this is a not valid sequence. It is a not valid. For example, if it is 0, for example, then it is a valid bit. So that means I am saying that, note that LSB is considered first. Considered. If I say that, note, If MSB is considered first, then whatever you said is correct. Okay. Okay. So therefore, I am saying that the first LSB bit I have considered, LSB point of view, I have discussed about here. Okay, fine. So therefore, this is all about LSB bit position. So this one and my previous one is also LSB related. Okay, fine. So therefore, valid bit or not valid bit with respect to the position of the bit, I am telling you, we have talked about it. Okay, consider that LSB position is the first thing that is entered into your digital system. Okay, now, so being considering the well, LSB is considered the first. Okay, this is considered first. The second one is I'm talking about is a put it as a comment. Next one is overlapping sequence. Overlapping sequence. So these two things also we have to remember. Okay. So therefore, this point is important, and these 2 points are also important for us. Okay. Now let us go for this background. We'll apply the state diagram. Okay. So let me call the state of the system is S0. Okay, so any name that we can give also. Okay, so therefore this is the state of a system. If input is equal to 0, for example, if input is equal to 0, so as I mentioned that 0 is actually not valid bit actually with respect to the LSB. Okay, therefore it cannot change the state of a system. It remains in the same state. It remains in the same state is represented in this way, provided x is equal to logic 0. Right? Okay. Okay. So did we get the output y? No. So the y output is equal to 0. Y is not 1. It is 0 only. So this is the representation. Okay. So any state diagram is represented in this way. It is called Mealy FSM. Mealy FSM. It is called Mealy FSM. So representation. The output we have to mention. Sorry, input we have to mention. Give the forward slash. Write the output also. So this is the state of the system. It is the state of the system. Now, yeah, first bit is completed. So first bit possibility 0 is completed. Now it has come 1. For example, 1 has come instead of logic 0. Yes, obviously the digital system will change its state and it will move to the next state that is called S1. That is called S1. Right? So this is called S1. When it will go to the state X1, if X is equal to 1, instead of the logic 0, if you're there in the state, if logic 0, you are there in the same state. If it is 1, it go to the next state because the state will changes. Did we get the output logic 1? No, output is equal to logic 0 only because 3 bits are not completed so far. Agreed? Okay, fine. Next one is that means you have detected logic 1 at this point. So if you are there in this state 1, what does it mean? One is detected. So okay, one detection position. This is now the second bit will come into the picture. The second bit possibilities logic 0 may come. The second bit maybe logic 1 may come. So second bit anedi two possibilities vachinayi manaki. Again, logic 1 can be possible, logic 0 can be possible. Okay. For example, if it is a logic 0, what will happen? If it is a logic 0, what will happen? So since actually logic 0 is not a valid bit sequence, to start a new sequence, అక్కడ నుంచి కొత్త sequence start చేయడానికి ఆస్కారం లేదు because it is a non-valid bit. But can we take both together? since it is a overlapping sequence. Yeah. So 1-0 can be observed here. 1-0 can be observed here. So 1-0 can be observed here. In this purple color, I have mentioned that 1-0 can be observed. So it is a valid sequence. 1-0 is a valid sequence. If it is 1-0 is a valid sequence, because of 0 it's not a valid, but 1-0 is a valid sequence. Therefore, it can change its state called S2. Okay. 2 points we have to remember. One point is that if you want to change a state from one state to another state, two possibilities we have to think about. One thing is that it should be a valid bit. Okay, if it is a valid bit, it will move to the second state. If it is not a valid bit, but a sequence can be a valid or not, we need to check. If bit is not a sequence, bit cannot be a sequence. If 2 bits are there, then we can call it as a set of 2 bits can be a sequence. If that sequence is a valid sequence, it can also move to the next state. Okay, so therefore note, I will write the note here. So when we need to move to the state can change in 2 ways. One way is one way. If it is a valid bit, if the bit is valid bit, if the bit is valid bit. Okay, so if the bit is valid bit or not, that will be decided first case. Most of the cases, most applicable. The second one is if the sequence is valid sequence. If the sequence is valid sequence. Okay, so these are the two ways where we can change the state. Okay, fine. Okay, now we say that if x is equal to logic 0, but 3 bits are not completed, the output is equal to 0, but it moved to the next state. Okay, fine. What about it is 1-0? Okay, so if it is a logic 1 has come, logic 1 is a valid bit. Okay, so it has to move to the forward. Okay, but already we have forwarded the 1 bit by S2 to the S2 side. But where it has to move? So that means 1 is already detected. Again, we need not to detect anything there. Therefore, I can say that please be there at this position. Please be there at this position since I have detected. Okay. Therefore, it says that x is equal to 1 already detected. Therefore, the detected state only ikkade untundi. By plus 0. Okay. So therefore, this particular state మనం ఏమనొచ్చంటే detected one state. Detected. It is a detected state. One detected state అని కూడా అనొచ్చు. One detected state. దీన్ని ఏమంటామంటే మనం therefore now here we observe that here we already decided 1-0 we have detected, right? So the third possibility is either logic 0, it may be logic 1. అంతేనా? This is what we can observe. So this state is called 1-0 detected state. 1-0 detected state. Okay, so therefore we observe that 1-0-0 is not a valid bit, therefore I cannot move forward. But I can say that these three I need to consider. So again, I need to talk about 0-0 sequence because of overlapping. It is also not valid. 1-0-0 altogether, it is also not a valid sequence. Bit is not a valid bit. Sequence is also not a valid bit. Therefore, what it has to do? It cannot do anything. Just it will be remains there in the previous state. That means the initial state valid bit is also not a valid. Sequence is also not a valid. Therefore, it come back to the initial state. So therefore, it is called x is equal to 0, but y is logic 0. Right now, Now, what about 101 sequence then? Okay, as we say that 1 is a valid bit, fine, it has to move forward. Okay, but where it has to go? So if it is a 1 is a valid bit, we need not think about previous bits. ఇక్కడ we చూసుకోవాల్సిన అవసరం లేదు. ఎందుకంటే అదే valid bit కాబట్టి అక్కడ నుంచి కొత్త సీక్వెన్స్ స్టార్ట్ చేయొచ్చు కదా. అవును. So when we can say that 1 itself can start a new sequence, that means where 1 is detected actually in S1 state. In S1 state. Therefore, what it has to do, it come back to the state 1 because there we can start a new sequence onwards. Okay. Therefore, I can say that here is x is equal to 1, but 3 bits are completed. Therefore, y is equal to 1 here again. It is y is 1 is here. Okay. Therefore, this entire sequence is started, completed. That's the reason why y is equal to 1. Okay. So therefore, when the moment, if suppose here is 0 has come here, for example, sorry, ఇక్కడ మనకు 0 వచ్చింది అనుకో, ఫర్ ఎగ్జాంపుల్ ఎక్కడ నుంచి సీక్వెన్స్ స్టార్ట్ చేస్తాను అన్నమాట. అంటే ఇక్కడ నుంచి జస్ట్ S1 నుంచి స్టార్ట్ చేస్తాను నేను కొత్త సీక్వెన్స్. I can start new sequence from S1 onwards. Agreed? So this is how we can represent very effectively the sequence detector with the help of state diagram. Okay. So this type of notation, we can call it as Mealy FSM. It is called as Mealy FSM. So let us write quickly the VLSI program for this one. As everybody knows that whenever we are talking about a sequence detector, it is called a sequential circuit. A sequential circuit consisting of 2 parts. One is a combinational part. Next one is a memory part. Okay. So this memory part is similar to that of D flip-flop. Okay. Okay. Where is it is there? Yeah. So this is called memory part. This is okay, I can write it very easily. So this represents the combinational part, and some is represent the memory part. Memory. Okay. The output of this one is connected here. The output of this one is connected here. What is the input for this one? So this combination circuits requires X input, and it will produce Y output. Okay. So therefore, only we have a clock signal here. Only we have reset signal here. Okay. All together, it's a sequential circuit. So altogether, this is a simple sequential circuit. Okay, it's a simple sequential circuit. We write the VLSI program for this one. In the previous class, we have already seen how to write this one. Okay, shall we write quickly? The question is that how many number of flip-flops are required to realize a memory? Anyone from the class? Anyone from the class? How many number of flip-flops are required in a memory? Anyone from the class? How many states are there? How many states? 3 states are there. To represent the 3 states, how many number of bits are required? Minimum 2. 2 is more than sufficient, right? 2 bits తీసుకున్నాం అనుకోండి 4 స్టేట్స్ వస్తాయి. కాబట్టి నాకు 3 స్టేట్సే కావాలి. 1 తీసుకుంటే అవకాశం లేదు. ఎందుకంటే స్టేట్ మిగిలిపోవచ్చు కానీ it is possible to state maybe, but okay, in that sense we have to use 2 bits. Okay, one is only 2 states can be represented, third bit we are eliminating, so then we cannot realize the sequence. But two bits, 4 states can be possible. Unused state can be say that it will be the initial state. It can be possible. Okay. Okay. Now let us write quickly to document. Please don't mind. I will take the previous program. I want to modify necessary things in this, okay, without change my affect my sequence of time. So okay, I can test you. Okay, here is good. What are the other things that we need to write here? Here it requires input also. It requires input X, output Y. It doesn't require. Agreed? Okay, fine. The input I have to mention. The input I have to mention called X. The output is Y, right? What is the size now? Size should be 1 down to 0. Y. Y, agreed? Okay. So therefore, the internal state is also a 2-bit size. It is also a 2-bit size, right? So this is called NS I'm writing. Here it is called PS I'm writing. So NS and PS I'm writing is from 1 down to 0. Okay. So past each other is set, and of course I need to change this one. It is 2 down to 0, 2-bit of 0, 0. And there the present state is assigned by next state. So therefore, this is what it is completed. Now we talk about combinational part. Combinations are realized by using the always statement only, but how this is how I'm writing here. And one more thing I forgot here is AND case. So please remember that you have to write AND case. Don't give space between AND and case. Okay. Now it is 3-bit size, right? It's called 2-bit of 0, 0. It is all 2 bits only. Okay. Okay. Two bit of 0, 0, 1 updu. For example, I'm writing this. This is a sequence S1 right for the time being. Okay, this is called 0, 0 state. It is called 0, 1 state. This is called 1, 0 state. Directly S1, S0, S1, S2 also we can place it there. I will tell you the point later on. Okay, for the time being, just you identify that. S0 stands for 0, 0. S1 stands for 0, 1. S2 stands for 1, 0. Please. Later, I will change the parameter values. Okay, I want to remove these things. Okay. Delete. Okay, so I write again. For example, if you're there in this 0, 1 position, right? 0, 1 lo next state next state should be 2-bit of 1, 0 kelali. Ade ganaka meer 2-bit of S0 lo unnaru next state should be 2-bit of 0, 0. For all other cases, that means here is the coming to the picture. For all other cases, there's a 4 state also, maybe 1, 1 state also. For all these cases, what is the next state? NS is equal to 2-bit of 0, 0. Last class. Let me check once. This is also a change. In the last class, change this one also. Instead of the Q, it should be NS. It should be NS. Okay, fine. Next, yeah, that's it. Okay. Then This is where we have to be kept here.
So,
Yes. Okay. We have two always blocks for combination block and memory.
so
Somebody please. Yes. Yeah, now it's fine. I hope there is no disturbance now. Okay. So the class is completed with this Verilla program. Please try to write the test bench for it. Please try to write the test bench for the counter as well as this one. Counter takes a very less time. You please try to do this one. Okay. I have already the test bench and all these things. Just to go through it once. Not written, but you please try to do it. Okay. If not, tomorrow I will wait for the next class. I will try to write for the test benches for this. Okay. This is what the to discuss. If you have any doubt, please just send it through the WhatsApp, maybe some other medium. The class notes is posted in modules platform, as well as class, whatever the classes that I have discussed about all these things, I have mentioned there. Remaining classes you can see in my YouTube channel. That's it for the today's. Stop here today. If you have any queries, you can ask. Yeah, can you send the attendance? Okay.
yes, sir. Yes, sir.